Hello, welcome back. In this segment, I will explain an algorithm to perform reachability analysis from a given source to a sink. For example, let's say from node 1 to node 3. Node 1 is the source, node 3 is the sink. We need to extract a subgraph that will help us to reach destination 3 from source 1. As we can see easily in this case, right? It's 1, 2, 6, 3, this path. Or from 1, we can directly reach 3. This is another path. Okay. How do we programmatically extract a subgraph given this is, for example, the source and this is the target? You can have multiple source, multiple target. The algorithm that I explained will be generalizable. But let's start with one source and one sink. In the previous segment, we discussed how to reach a given sink. For example, we know how to reach 3. That was possible easily just by doing simple relational algebraic operation. All right, so the first step is to figure out from 1, what are the possible reachable nodes? Okay, using relational algebraic operator, we will find out. And then from 3, what are the nodes that can reach 3? And then we ask, what are the possible ways one can reach 3? So we have 2 subgraphs, and then we intersect the subgraphs to form source to sink subgraph. Okay. First step is to compute relational transitive closure, which we already discussed during the previous segment for the example. And I will save it to trans.rel file. Now the transitive closure is ready. Our goal is to do source from 1 to sink number 5. How do we do the from 1? From 1 is simple, actually. We say create an element and we pipe it to something called rel dom r. Okay. What is the meaning of rel dom r? It means restrict the domain of a relation to a particular set. The set here is only 1. Yeah. For example, if you take the demo.rel, the graph that I have shown, when you restrict the domain to 1, the first column is always 1. That is what you're saying. The first column is 1. Other than that, all other operators are something that we already seen. So we can now very quickly go ahead and write the full query. Set q1 rel dom r, but we will be doing restriction of the domain on the transitive closure. Okay, this will tell us all possible nodes that are reachable from 1. And then what are we going to do? We will identify all nodes that are, now you have 1, 2, 6, 3. These are the nodes that are involved in reachability from 1, okay, including 1, of course. Okay. So carriage of a relation is just a union of domain and range. And now we can just restrict the original relation, the demo relation, right, to 1, 6, 3, 2. Okay. So these are the 4 possible edges we would need to have a subgraph starting from 1. Okay. We can save it to a file. Let me call it from1.rel. Okay. Let me copy this and show it to you what I mean by reachable from 1. So if it's reachable from 1, it means only this subgraph, right? 1, 2, 6, 3. These are the 4 nodes that should be involved in any graph that is reachable from 1. Okay. The reachability analysis showed 6, 3, which is this edge, 6, 3. Let me 6, 3, 2, 6, 1, 3, and 1, 2. These are the 4 nodes and 4 edges for the subgraph starting from 1. Okay. And now we need to figure out another subgraph that is targeting node number 3. So reaching node number 3. And then we take intersection of those 2 graphs. That should be good enough for us. Okay. So we'll find another graph, all possible ways to reach node number 3. How do we do that? Which we did already in the previous segment. So I'll be just very quick now. 2, 3, yeah. Reaching to 3. And the range is now restricted to 3. That's all. And now we have another subgraph. Now we have 2 subgraphs. Okay. Let me show you what is this subgraph, right? So this is having 5 nodes, 5 edges rather, all possible ways to reach node 3 has 5 edges. You can confirm by looking at the graph again. All I'm doing here is all possible ways to reach node number 3. Okay, you have 1, 2, 3, 4, 5. 5 different edges are needed to reach node number 3. We can confirm by looking at the graph. All possible ways to reach node number 3 is essentially 4, 1, 2, 6, 3. These are the 5 nodes and these are the 5 edges. 1, 2, 3, 4, 5. So we have now 2 graphs. We can now intersect them to form the reachability from 1 to 3. Okay, so let's do that. All we need to do is set intersection. Remember, relation is just a set, so I can do relation intersection, which is another algebraic operator, from 1 and 2, 3. Okay, so you have 2, 6, 1, 2, 1, 3, 6, 3. Let me copy this. Okay, so the resulting graph we have is 2, 6. This is 2, 6. 1, 2. Yeah, this is 1, 2. 1, 3. Yes. And 6, 3. So all of these 4 edges and 4 nodes, they form a reachability graph from 1 to node number 3. This is exactly what I meant by reachability from a given source to a given target. All right. We can easily extend this algorithm by adding more sources, more sinks. All you have to do is just add an extra element to the set. I'll show you what I mean by that. You see here, I put only one set, right? 3. That means if you wanted to have more reachability to different nodes, then you can add more nodes here. You can add 3, 4, 5, whatever you like. This problem comes often in reverse engineering where you are understanding some program and you wanted to figure out what are the different ways I can reach from a given source to a given sink. You have a graph and you apply relational operators like I did to form a subgraph to answer your question. Okay, that's all. Thank you very much for your attention.